Hello everyone, this is Mr. Bowman, and in section 10.2 we are going to compare population means similar to how we compared population proportions in section 10.1. So to start out with, we are going to look at a scenario here, and we're going to use that as the basis of our discussion. So in this particular situation, it's about batteries and two companies that produce batteries. Suppose you want to compare the battery life between Weitzel Core Energy batteries and a generic brand. You design an experiment where you test battery life by playing the same song at the same volume in your MP3 player until it no longer plays. You randomly purchase 6 sets of each type of battery to run this test. You then test each of these 12 sets and record the time it takes for the MP3 player to quit working in the table below. What I would like you to do is read question A and B, pause the video, answer those, and when you're done, come back, unpause the video, and we'll discuss that. So hopefully you've decided that the populations are all Weitzel Core Energy batteries and all generic batteries, and hopefully you also decided that we are referring to the mean lifetimes of those batteries. So what we're going to do with this situation is we're going to start out kind of old school with this, and we're going to take a look at the 5-number summaries of both of these samples and also look at the modified box plots of them and see if we can answer some questions based on that. So we're going to do a side-by-side comparison of the data and see what the data might lead us to conclude. You're looking at the 5-number summaries for both samples, which in and of themselves aren't really that informative. It's much easier to look at the plots of the data, so I'm going to bring that up on my calculator. And on the top in blue, we have a modified box plot for the Weitzel Core Energy batteries, the sample of 6, and below that we have the box plot for the 6 generic batteries. First question asks if there are any outliers in the data. Well, clearly there are outliers in the data. You can see that from the generic brand batteries. It has one outlier and one outlier at the low end, one outlier at the high end. And what can you conclude from these statistics? Well, I think it would be relatively easy to conclude that based on the statistics alone, that the red distribution has a significantly higher median, and also likely a higher mean than the blue or the Weitzel Core Energy batteries. Remember, if we were going to write that up, we would have to be specific about that. So the generic brand has 2 outliers, one at 190.7 and one at 222.5, and the data does suggest a difference in the average lives of the batteries, but the samples are small and there are outliers. The issue with using the old school approach is we don't have any level of confidence in our conclusion. We just have a conclusion. So what we'd like to be able to do is establish some level of confidence, and we're going to do that by way of a confidence interval. So we're going to talk about constructing confidence intervals for the difference of 2 population means, but before we do that, we want to establish some properties regarding the sampling distribution of the difference of the sample means, and we will start out by looking at what the mean and the standard deviation of that sampling distribution is. So in a method similar to what we did for the mean and the standard deviation of the difference of sample proportions, we're going to establish the mean and the standard deviation of the difference of sample means. So you can think of 2 sample means as 2 random variables because the samples are randomly selected, and we're going to start out by assuming that the samples are independent of each other. So what we really want to find is we want to find the mean of the difference x1 bar minus x2 bar. And since that is a transformation or a combination of those two random variables. It's really just a difference of the two means, mu x1 minus mu x bar 2. But those are unbiased estimators of the population, their corresponding populations, so that's mu1 minus mu2. The standard deviation, if you remember, we can add variances, but we can only add them if they're independent. That's why the check that the two samples are independent of each other is so important. So the variance of the sampling distribution of the difference of sample means is equal to the sum of the two individual variances, and the individual variances are just the squares of their standard deviations. So their standard deviations, remember, were the population standard deviations divided by the square root of the sample sizes, but we need to square those to give us the variance. We're going to do that for population 2 as well. And that gives us sigma 1 squared over n1 plus sigma 2 squared over n2. And to find the standard deviation, we would take the square root of what we just found. So it would be the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And remember, that depends on the condition that the two random samples are independent of each other. So this approach to finding the mean, the standard deviation, and the shape of the sampling distribution has become kind of routine. So what we're going to do is we're going to assume we have a normal sampling distribution for the difference of two sample means, and we're going to sketch that out. So at the center of this would be the mean, which is the difference of the two population means, and the standard deviation would be equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Let's take a look at a summary of everything we just talked about. So the sampling distribution of the difference of the sample means. First, if we take a simple random sample from each population and they're independent of each other, the shape of the sampling distribution of the difference of sample means will be normal if the two individual populations are approximately normal, or if the sample sizes are at least 30. We can invoke the central limit theorem for each of the individual sampling distributions, and therefore the shape of the difference of the sample means sampling distribution would also be normal. The center will be equal to the difference of the population means, and the standard deviation would be given by this formula right here. So we have a normal distribution that looks like this. Let's take this information and let's apply it to this particular problem. So we have a fast food restaurant. It uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid dispensed by the machine follows a normal distribution with a mean of 27 ounces and a standard deviation of 0.8 ounces. When the medium setting is chosen, the amount of liquid dispensed follows a normal distribution with a mean of 17 ounces and a standard deviation of 1/2 ounce. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in a random sample of 25 cups filled with the medium setting and a separate random sample of 20 cups filled with the large setting. Let x1 bar minus x2 bar be the difference in the sample mean amounts of liquid under the two settings, large minus medium. We could do this in either order. We could do large minus medium or medium minus large. but you just have to pay attention to the order and think about what that implies. So what is the shape of the sampling distribution of the difference of the sample means? Well, in the problem, it was stated that the two populations are normally distributed. Even though the sample sizes are not at least 30, we don't have to invoke the central limit theorem. So the sampling distribution of the difference of these sample means is normal because both populations are normal. Find the mean and the standard deviation of the sampling distribution. So the mean would be mu L minus mu M, large minus medium, and that is going to be 27 minus 17, which is equal to 10. The standard deviation is going to be L minus M is going to be given by the following. The standard deviation of the large population, 0.8, squared over sample size for the large, which was 25, plus the standard deviation for the medium, which was 0.5, squared over the sample size of 20. To 4 decimal places, that turns out to be 0.2049. Find the probability that the difference in two sample means, x1 bar minus x2 bar, is more than 12 ounces. Show your work. So I want to illustrate this with a picture. So we're taking large minus medium, so the mean is 10, and we're asking what is the probability that the difference in two sample means is more than 12. So there's 12. So we're finding this area up here. We have a normal distribution. We're using Z because we know the population standard deviations. This, under most circumstances, is not realistic. So Z is equal to 12 minus 10 over 0.2049. That turns out to be a Z-score of 9.759, which, as you know, is going to give you an extremely small probability up here. This area is going to be approximately 0. So, based on your answer to part C, would you be surprised if the difference in the mean amount of liquid dispensed in two samples was 12 ounces? Yes. Effectively, what we found was a p-value here. So, if the difference in the two population means is really 10, then the chance of getting a sample mean with a difference of 12 or more is approximately 0. So, yes, we would be surprised if we got a sample mean with a difference of 12 ounces or more. So that summarizes and works through an example of the sampling distribution of the difference of sample means. What I want to do next is I want to talk about conditions and then go on to construct some confidence intervals and interpret them. So, what about the conditions? First of all, we need to have two simple random samples from two distinct populations. Independence, the two random samples from the two populations must be independent of each other. Otherwise, we cannot apply the formula for combining the two variances to find the standard deviation. But we also need to make sure that the 10% condition within each sample still applies. Otherwise, we wouldn't be able to calculate the individual standard deviations. And both populations have to be normally distributed, or both sample sizes have to be at least 30. So we are asked to check that these conditions are met for the battery problem. So we're going to go through these. If you go back and you reread the details of the battery problems, you will see that both sets of batteries were randomly selected. So we meet that condition for both samples. Because of the random selection, I think it's reasonable to conclude that the two samples are independent of each other because they come from two different manufacturers. The 10% condition within each sample. Sample sizes were 6. 6 is easily less than 10% of either types of batteries populations. Therefore, we can assume independence within each sample. The normality conditions are not met. It was not stated that either population was normal, and both sample sizes were small. In addition, the generic brand had outliers. If, however, the conditions had been met, we could construct a confidence interval using this formula. Basically, the left-hand part here is the statistic. This is the margin of error, and the margin of error consists of two parts, the critical value and the second part being the standard error of the statistic. Notice that the standard error is replacing the standard deviation of the sampling distribution of the difference of the sample means, because if we were constructing a confidence interval to estimate the difference in the two population means, we would not know the population standard deviations, but we would know the sample standard deviations. In addition, since we have switched over to using sample standard deviations, we are also going to switch over to using a t-distribution. So what I'd like to do next is take you through the process of constructing the confidence interval for our battery problem. There's one thing that we have to talk about first before we do that, and that is, how do we calculate the degrees of freedom for this situation? Is it based on the first sample or the second sample, or a combination of both? So as you recall, from constructing confidence intervals for a single mean, when we don't know the population standard deviation, we have to use a t-distribution. And to use a t-distribution, we have to know the degrees of freedom. And normally that was based on the sample size minus 1. When you are constructing a confidence interval for the difference in two sample means, you have two options for finding the degrees of freedom, which obviously you need to know so that you can use the correct critical value. So one option is to take the smaller of the two sample sizes and subtract 1 and use that degree of freedom. That will give you the largest critical value, and you can use that. That is the method I would use if I was not using the built-in function in my calculator. If I am using the built-in function in my calculator, there is a very complicated formula which you do not need to know. This formula right here, which you see in front of you, is what is used to calculate the degrees of freedom. That is actually a less conservative approach, but it's a more accurate approach. So you got, again, two options. Conservative approach, use the smaller of the two sample sizes minus 1, or use technology, and the technology is going to come up with an answer for you. My recommendation is use technology because I think it's easier and you're less likely to make mistakes. I am going to demonstrate both ways of doing it because I know some of you don't use the built-in functions in the calculator and some of you do. So we'll start with the method of not using the built-in function in the calculator. Since both sample sizes are 6, our degrees of freedom would be equal to 5. The 95% confidence interval, I will leave it up to you to either look up on the table using a t-distribution or using inverse t on your calculator. The t critical value would be equal to 2.57. And our confidence interval is going to be generic brand minus Weitzel core. So from the given information or from our calculators earlier, we would have a sample mean of 206.2 from the generic minus 187.43 from Weitzel core, plus or minus our critical value of 2.57 times the standard error, which is 10.3 quantity squared over sample size 1, which was 6, plus 14.61 squared over sample size 6, and you can see that that comes out to negative 0.17 to 37.35. And how would we interpret that? This you have to pay close attention to. We took generic minus Weitzel core, so we would interpret that something like this. We are 95% confident that generic batteries last anywhere from 0.17 minutes less to 37.35 minutes more than Weitzel core energy batteries. Now we're going to do the same thing using our calculator, and you will see with the calculator that the degrees of freedom will turn out to be approximately 9, and so what that turns out is that the critical value, which we can find by taking inverse t of 0.975 comma 9 is approximately 2.26. So you'll see that's a more accurate but a less conservative approach. I'm going to show you the calculator in just a minute. The confidence interval we're going to get, the 95% confidence interval we're going to get for this same situation is going to be from 2.07 to 35.1. And what you notice there is that in the more conservative approach, the less accurate approach, our confidence interval did contain 0, and in this case it didn't. So that's a pretty significant difference here. Again, the way we would interpret our new confidence interval, since we took generic minus Weitzel core, it would go like this. We are 95% confident that generic batteries last anywhere from 2.07 minutes to 35.1 minutes more than Weitzel core batteries. All right, so back to where we started with our modified box plots. We had evidence that the generic batteries last longer. We just didn't know how to quantify how strong that evidence was. So what we're going to do is we're going to do a 2-sample t interval for the difference of the population means. And we're going to do a 95% confidence interval. So we've already got the data in there. Stat, go over to tests. Again, look for the test that makes sense. Down at the bottom, you'll see 2samp zint. If we go a little bit further down to number 10, I believe it is, we're going to see 2sample tint. That's the one we want. So we select that. We actually have data in our calculator, so we're going to select that. The data, remember, we got to pay attention to the order here. So we want to do generic minus Weitzel core. Our Weitzel core data is in list 1, our generic is in list 2, so we're going to leave this the way it is, but we're going to have to deal with this later on. Our level of confidence is 0.95, and to pool or not to pool. And this is an interesting question. What it comes down to is the following. If you had evidence that the two population standard deviations were the same, then you would say you would pool. To do that, you would have to do a test to compare the two population standard deviations. It's called an F-test. We're not going to get into that. So what you should do is you should always say no when it's pooling, and then we're going to go ahead and calculate this and see what kind of results we get. Okay, so this is important. Since the calculator defaults to x1 bar minus x2 bar, and we switch the order from the way I wrote it in the notes a moment ago, you will see that we got a confidence interval that went from negative 35.1 to negative 2.07, which is basically the opposite of what I got. Same degrees of freedom, same sample means, same sample standard deviations, and so on. So this doesn't change our conclusion. It just changes the way we write our confidence interval. So remember these numbers, negative 35.1 to negative 2.07. Back in OneNote here, I wrote it from 2.07 to 35.1. We would interpret it the same way. We are 95% confident that generic batteries have a mean lifetime that's anywhere from 2.07 to 35.1 minutes greater than the mean lifetime of Weitzel Corp batteries. All right, the last thing I would like you to do is pause the video, work through this, check your understanding, and then unpause the video and we will discuss the solution to it. All right, so the first thing I want to point out is that this problem says using your calculator, construct and interpret a 99% confidence interval for the difference in the mean wheat prices in July and in September. So I am not going to tell you, the College Board is not going to tell you, you need to check conditions unless it says explicitly no need to check conditions or assume that the conditions have been met. So random samples are both stated. Samples are stated to be independent. It's reasonable that 90 and 45 were both less than 10% of wheat producers when the samples were taken, and normality condition is met as both sample sizes are greater than 30. Since we're using the calculator, we're going to use the more accurate degrees of freedom. So using the calculator would give us approximately 100 degrees of freedom. And you still have to show your work. So one of the things you have to do is you have to go back and you have to find the critical value. So you do the test first. The calculator tells you degrees of freedom is approximately 100. You work backward, since we're doing a 95% confidence interval, to find the critical value. We're going to do inverse t of 0.995 using the calculated degrees of freedom. We get a critical value of 2.63. You have to show your work. So this 2.63 has to go down here, write down first mean minus the second mean plus or minus the critical value times the standard error, and then write your confidence interval, and then interpret your confidence interval in context. So the interpretation is we are 99% confident that the mean price per bushel of wheat in September was anywhere from 56 cents to 76 cents higher than the mean July price.